Okay, we're going to continue on here, chapter 2, I think. So last time we really got into equalities, conversion factors, and dimensional analysis. So remember that we use an equality which is essentially two different values, which are on two unit scales, but does represent really the same amount of something. So like we have 12 inches is equal to 1 foot. That would obviously be our equality. From any equality that we have, we can write two conversion factors. And really, conversion factors are nothing more than just fractions. So we could say, for example, 12 inches over 1 foot, or 1 foot over 12 inches. And these would be our conversion factors that we could use. So when we do set up something to solve, we do want to do dimensional analysis, which is really unit-based sort of calculations, where if we have a certain unit that we do not want, we use a factor. And it's always opposites, as we talked about last time. So again, although this is not really written as a fraction, that sort of first unit there is up on top. So really, it makes it pretty simple in terms of how to do the math, which is I just need to put the same unit in the opposite location. So we would use the same unit that we want to get rid of in the opposite location, and whatever unit maybe we're looking for would end up on top. Essentially, these units will cancel because what we're doing mathematically is multiplying anything on the top and dividing whatever is on the bottom. So essentially, as we talked about last time, if we took 2 divided by 2, that would equal 1. So if we had this unit up on top divided by the same unit, that will equal 1, which means they essentially cancel each other out. So that's sort of the idea there. So if we had 42.5 inches and we wanted to know how many feet that would be, we would start the problem with what was given to us. Once again, here we would look at it and we want to use a conversion factor where inches would be in the opposite location, which would be on the bottom. And we would want to use the guy over there again on the right. And we would have 1 foot is 12 inches. Once again, the inches would cancel. The units that we're looking to be left with there are up on top, which is typically what you want if you have one unit that you're solving for. It should be up on top by itself. And we would multiply basically, in this case, 42.5 times 1, and then divide it by 12 and hit equals. And again, we would get something on our calculator, 3.54166667. And the units here would be feet. Now, in terms of significant figures, the other thing that we were talking about is when we do use these sort of equalities and these conversion factors that come from equalities, we maybe have to look at the significant figures or may not have to look at it. In a case like this would be considered an exact number. And that's always going to happen when you kind of go from like English units to English units or US to US. And also when you go metric to metric. So any type of sort of metric to metric conversion as well would be considered an exact number. Remember, exact numbers pretty much have an unlimited number of significant figures. So when we're doing calculations, we really don't worry about them in terms of our answer when we come across them. The one place where you really do have to look at sort of a conversion factor is really when you cross over from English to metrics in terms of using a conversion factor that comes from that. Other than the 1 inch is exactly 2.54 centimeters, but pretty much all other sort of metric to English or metric to US conversions, you should look at it. So in this particular case, we wouldn't look at that guy, which means really significant figure wise, that is the only number that we have to look at, and we do need to look at it. And that would be 3 significant figures, which means we would want to go here, and we would want to then round this to something like 3.54 feet in this particular case would be the proper answer with the proper number of significant figures. Other things that sometimes occur that I think we might have also talked about is if you are given a sort of conversion factor within a problem, you should probably look at the significant figures in that conversion factor. And again, usually the conversion factor that you may have to look at, usually one of the numbers will be 1 and the other number will be another number. And you obviously look at the other number, not the 1, when you're looking at significant figures. Any questions on that there? All right, so I think we left off somewhere in this. Did we do this one? No. We did the one before, right? With the, I remember one with the pill or something, right? And how many tablets? Is that sort of where we ended up on? All right, so let's start here. Your pace on the treadmill is 65 meters per minute. How many minutes is it going to take you to walk a distance of 7.5 kilometers? Kilo is 10 to the 3, right? All right, take a few moments there, set it up with dimensional analysis. Think about the equalities. Think about your pathway to get you there. Think about your answer. Yes. All right, let's take a look and see. So we got a couple of things given to us. We want to know how many minutes, which obviously is a unit of time. So we need to get to a unit of time. We are given really a sort of a conversion per minute. Use in this fashion, we could all flip it around and throw the minutes up there on the bottom. So again, sort of a conversion factor given to us. That's actually a rate, which has like distance and time. That's what we're going to really use to go from distance into time, which is ultimately what we're looking for. We are going a distance of 7.5 kilometers. So we do have some unit issues here. Our distance in this guy is kilometers. Our units here in this guy is meters. So we do have to do a conversion. Once again, you can do either one. You can either convert the meters to kilometers or you convert the kilometers to meters. I'm going to convert the kilometers to meters. That way I could just use the conversion factor the way it is. Kilo means, right, in 1 kilometer, there is 10 to the 3 meters, or that's really 1,000, right? Meters in a kilometer is the same thing, whichever way you want to use it. That's going to give us really 2 conversion factors of 1 kilometer over 1,000 meters, or 1,000 meters over 1 kilometer. So I'm going to start with my distance here and go 7.5 kilometers. Once again, not really written as a fraction, but if we want to think about it, it's up on top. And again, that makes just the whole math part pretty easy. I need to go opposite, right? So I should use the conversion factor on the left or right here. One on the right, right? So that has the opposite location for the kilometers on the bottom and 1,000 up on top. That's going to get rid of my kilometers and convert me into meters. And we're basically just going to take 7.5 and times it. If you hit the times button, that would help by 1,000 and not 100. So let's use 7.5 times 1,000. Get it here. All right. So 7,500 meters at this point. Now I have it in meters, which is good because really this guy is in meters. So now I could use that to go from really distance here to time. So again, if you're not sure how to use it, just think about opposites. So this guy again is still up on top, which means when we come into the next spot, we need to go opposite. So once again, here on the right is what we're looking for. That's going to put the meters in the opposite location on the bottom. And minutes are up on top. And actually, in this case, the meters will cancel. That's going to leave us minutes. And that's actually the unit of time we're looking for, right? So what's left here again is we're going to multiply whatever's on top and come back and divide by what is on the bottom. So really it's just 7,500 divided by 65. And that's going to give me on my calculator 115.3846154, and the units are minutes. And clearly we'll never leave an answer that many significant figures unless you like lines through your numbers. Yes, so don't leave that many. So let's talk about significant figures, right? So we should look over here, and that has 2 significant figures, right? Do I need to worry about this conversion? I don't. That's an exact number, which means really what I ended up with should have 2 significant figures, which actually in this case It actually does the way I wrote it, right? So that still has two significant figures. Now, should we worry about this conversion factor? The answer is yes, because that's specific to the problem, right? So it's not always 65 meters per minute, right? So we should look at it. And the only number that we have to look at here is the 65, which would also be two significant figures. So we're basically multiplying or dividing here two significant figures. Remember, right, when we multiply or divide, we look at significant figures, and it is the smallest number of significant figures, right? When we add and subtract, we look at decimal places, right? And it's the smallest number of decimal places. So you want to keep that in mind. So in this case, we actually should end up at two significant figures, which is right about there, yeah? And that looks like a 5 after that, which means I really should round up to $1.20 here, yeah? Should I put a decimal at the end of that? I should not, because then it would have three significant figures, right? So 120, no decimal, or if you want to do a little scientific notation action on that, 1.2 times 10 to the 2 would also work if you wanted to. Question on that calculation there. Yeah. So I think we talked about it last time, and sometimes people are resistant to set things up with dimensional analysis, even though that's the way you need to show your work in this class. But again, it really does make sort of like, should I multiply, should I divide? It kind of takes it out of the picture in a sense, as long as you put everything opposite and just remember everything on top gets multiplied, everything on the bottom gets divided. You don't have to worry about, am I dividing when I should be multiplying, and those type of things. So it's really important to sort of set it up like this. Any questions on that? All right, they agree too. That's pretty good. All right, that'd be kind of embarrassing if they didn't, I suppose. All right, let's try another one here. You go to AM/PM, go to the Thirst Oasis, get yourself a Diet Coke, 32 fluid ounces. How many gallons of Diet Coke did you drink? There's a few equalities that might be helpful, so see what you come up with. All right, let's take a look. So we're going to the Thirst Oasis there, 32 fluid ounces of Diet Coke, crushed ice or cubed ice, but I think everybody knows it's crushed ice, right? And we're going to see how many gallons that is. So as we talked about, there are multiple ways you could get to the answer depending on the conversion factors that you choose. So you just want to think about a logical, legitimate pathway, no conversions you made up, to kind of get you there. So in this case, we could go from fluid ounces to quarts over to gallons. So these are a couple of equalities that can get us there to where we need. From these equalities here, we could have a few conversion factors again to choose from. And again, as we talked about, we're not going to use all the conversion factors. We're just going to use whichever ones we need. So here we'll start with what was given to us, which is 32 fluid ounces. Once again, that's basically up on top. So we want the opposite. And that's going to be that conversion factor there, which will put our fluid ounces there on the opposite location. It gives us 1 quart. Once again, you could get an answer after you do the first conversion if you want to. I think we've talked about it as well. We don't want to round too much at that point. We want to kind of take a few digits extra than we need. Or you could just continue on with the calculation. Again, setting it up like this, fluid ounces on top and bottom would essentially cancel. And if we stop the calculation right at this point, we're in units of quarts. And again, we could clearly see at this point that the quarts are up on top. So that makes the next part of the calculation pretty easy. It just needs to go now on the bottom, right, to get rid of them. And that would make our choice of conversion factor pretty easy. I should use this conversion factor right here. And that would get me 4 quarts on the bottom and 1 gallon up on top. So again, not a lot of sort of thinking of, again, should I be dividing or multiplying at this point? If you set it up like this, which you should, all you have to remember is opposite. At this point, we're left with the units that we want. We're going to multiply everything here on top, which is not very much to multiply by since they're all ones. We're going to then come back and divide by what's on the bottom. As we might have talked about as well, I would divide by the first number, hit equals, divide by the second number, and hit equals, kind of do them separately, and you usually will get the right answer, all the time. We kind of punch it in that way. So taking 32 divided by 32 and divided by 4 gets us 0.25 gallons. And once again, That is the answer. It is not 1/4 because that makes me just think you're too lazy to divide out the number. Yes, and don't leave an answer as a fraction. Always divide it out and take it to the proper number of significant figures. Not too bad in this case, but I've had people sometimes give answers like 325 miles over 680 hours. Looks like a great answer. You don't want that. Yeah, so don't ever leave an answer in a fraction form. Divide it out. Significant figure wise, I'm thinking we really just got to look at this first number, which is 2, as the rest of them probably would fall under the exact number range there, and we would end up with 2 significant figures. Any questions on that one there? All right.
Do we have to transfer the result to like as 2 significant figures only?
Do you have to give the answer to 2 significant figures?
Yes.
You would in that case, because that's the proper number of significant figures. Yeah.
Is it 0.253?
0.25 is actually 2 significant figures only. This 0 is not significant because we haven't hit the first non-zero. Yeah, so we would start counting there at the 2, and that would give us 2. Other questions? All right, so let's take a look at another one here. Patient receives 5 pints of plasma. How many milliliters of plasma was given? Here's a few conversion factors that might be helpful, some conversion that you might want to use. So see what you come up with on this one. Okay, so let's take a look again. We want to think about a pathway, and with these equalities, that should get us there. We ultimately want to go from pints to milliliters, not many, but to milliliters there. So we can, one way is to go from pints to quarts, and then take our quarts to milliliters will get us there. Again, we have our sort of 4 conversion factors to choose from. We're going to use probably 2 of the 4 here to get us there. We'll start with what was given, which is 5 pints. And again, if we have 1 unit and that's the only unit given to us, it's essentially up on top, which is a good thing to remember. So now we just got to go from our pints to our quarts. I'm just going to think the opposite. So pints are on top. So it seems logical I should put pints in the opposite location here on the bottom. So I'm going to use that as my conversion factor. In 1 quart. Once again, if I laid up the calculation right at this point, the pints would cancel. The units I would be left with at this point are quarts, which is close to what I need. But once again, I need to go that next step. So again, by setting it up like this, clearly could see I put my quarts up on top and I want to get rid of quarts. So the easy choice is opposite location there, right? So we're going to take the conversion factor over there. On the right, it puts the quarts in the opposite location, 946 milliliters. Quarts are going to cancel. At this point, we're going to multiply what's on top. Make sure we hit equals at the end of that, since we got a couple of numbers happening at that point. We're then going to come back here and divide and then hit equals. Not really much to divide on that one on the last part there. So we're going to take 5 times 946 hit equals divided by 2. Going to give me 2365 milliliters. First off, any question on the setup here? Again, this is how you should show your work with the units and what's referred to as dimensional analysis. So you can see everything canceling out if you would like all the credit, which I imagine you do. And again, helpful when you're doing the calculation as well. Let's talk a little significant figures. I'm thinking we should look at this number, right? Which has how many? Let's have 2. Do I need to worry about this number or this conversion? How about this one? I do, right? So that's like a metric to English conversion. The number we want to look at is the actual number, the 946 here, which is 3, right? That means really my answer here should end up at 2. Again, since the dimensional analysis is pretty much all multiplying and dividing, it's always significant figures you're going to be looking at when you set it up like this and do this type of calculation. And again, it's always the smallest number of significant figures because frankly, that's your worst sort of measurement. That means I should end up here at actually something like 2,400 milliliters, right? No decimal, right? I could also do scientific notation if I wanted to, which would look something like this, I believe, right? So if you want to do a scientific notation. Any questions on that there? Again, reminders as we've been talking about, try not to round too much to the very end, but you should keep track of, your sort of significant figures as you go through the calculations along the way. All right, let's take a look maybe at one more here. I think. All right, you are stranded. You're stranded 125 miles away from home and you have no money. So you decide it looks like nice weather, no rain this week. You're going to walk it home. So you walk at an average of 55 feet per minute. How many days is it going to take you to get home? Provided you don't eat or sleep. All right, so see what you come up with. Some conversions that might be helpful, some equalities there. Okay, so let's see how you're doing. So this one is kind of similar to the treadmill one we did earlier. We have a distance that we want to go. We also have, again, a rate, which is basically a distance over time. And just like the previous one, that's what's going to allow us really to go from kind of distance into time as we're looking for days, right, which is a unit of time. We do have the same sort of issue. Our distance there is in miles and sort of our rates there is in feet. So we have different units. So once again, you could do the conversion like we talked about previously. In this case, you could take the miles to feet, or you could take the conversion factor there from feet to miles. I, again, am going to take this into feet first. That way I could use this as a conversion factor. And once again, if I needed to, I could also flip this around and put minutes up on top and 55.0 feet. And I think that's what it says on your handout there, 55.0, rather than just 55 even. So we'll do the feet conversion there to miles, or miles to feet, actually. So basically 1 mile is 5,280 feet, or 5,280 feet is 1 mile. So we'll take our 125 miles. We're going to put miles in the opposite location, which will be on the bottom there. And that's going to be 1 mile is 5,280 feet. Miles will cancel. Going to give us something like 125 times 5,280 feet. 660,000 feet. So I'm going to take that now, and now I could use it with my conversion factor, 660,000 feet. We're going to go feet on the bottom, so we will want to use it here on the right. And we'll do our 55 feet per minute. That is what's going to get rid of our distance here. And now we're our units, right, of minutes, which is close to what we want, but we do want days. So we could use our other sort of equality here to do this. And this is why, again, it's important to set it up like this so that we could clearly see minutes are on top. So we want to put minutes on the bottom here and 1 hour up on top so that they cancel. That will then give us hours, which again are on top, which we want to get rid of. We might have talked about it. It is only 24 hours in 1 day. So we'll take 24 hours on the bottom, 1 day on top. Again, opposite's going to cancel. We're going to multiply everything on top there and come back and divide what's on the bottom. So 660,000 basically times 1, going to divide it by 55, hit equals. Divided by 60, hit equals. And divided by 24 and hit equals. And that's going to give me 8.33 days as our answer. Again here, significant figure wise, this had 3 significant figures, which means technically, although I didn't write it like that, that number should have 3 significant figures, which means when I come here, that has 3. That has 3. This I do not need to worry about. That I do not need to worry about. So we should end up at 8.33 hours in this case, which would be 3 significant figures. Any questions on that? It would end up at 2 significant figures in that case. I changed it because I think on your paper or the handout it says 55.0. But if it was the original problem, like I had it up there at 55 feet per minute, you would look at that and that would be 2 significant figures, and you would end up actually with 2 in that case based off of that. Other questions? Yeah.
Instead of writing 66000 feet, continue the
You can. You could have started. You could have done this whole thing. If your question is, could I have just took that and just kind of continue there? You absolutely could have. Yeah, absolutely. Any questions on that there? Okay. Any questions on conversion factors or anything like that? Okay. So again, it's really important to make sure that you do set up these things properly so you can see everything canceling out. All right, the last thing we're going to talk about in this chapter is density. And density is basically the sort of property of matter that determines, for example, whether or not something will sink or float. And if something is more dense than, say, liquid water, it will sink. If something is less dense than liquid water, it will float, which is what we see here. We got some objects floating, and we clearly have some objects that are sinking. So density is basically the mass of a substance to its volume. It has a formula of D is equal to M divided by V. And we should think of this as a formula, which it is, and it is a formula that you do need to know. And we do have to rearrange it. So if we want to solve for volume, volume would be mass divided by density. We would basically multiply the volume to both sides, divide by the density to both sides is essentially what we did there. Now, if we want to solve for mass, mass would be the volume times the density. Sometimes people will remember this by the DMV triangle. Everybody loves the DMV. Density is mass over volume. Volume is mass over density. And mass is volume times density. So in terms of units for density, typically for solids and liquids, they have units of grams per milliliter or grams per cubic centimeter. Remember that a milliliter is equal to a cubic centimeter. It is a 1-to-1 relationship. We really don't come across it too much in this class, but when you deal with gases, the units of density for gases are typically grams per liter. I would say for us, pretty much these are going to be the 2 units that you will mostly see in terms of density. And really in terms of the volume, you really can get the volume a couple ways. You could get it by simply just taking a volume reading. So you put some liquid into a cylinder and take an actual correct volume reading. Remember that cubic centimeters is found by taking something like the length times the width times the height, where you measure them all in centimeters. And again, when you multiply them together, you get a volume like a cubic centimeter. So that's a very common way that you could find the volume of a solid object, like a cube or something like that, is to take those 3 sort of measurements. So the higher the density, typically particles are really packed together a lot closer. The lower the density, usually they're also kind of further apart from each other. One kind of common exception, for example, where that really doesn't hold true is something that we see probably most days is ice. Ice is the solid version of water. And when we put ice in our drink, it ends up where? Top, right? It ends up floating on top. And that's because when water comes together, it is actually held together by what is referred to as hydrogen bonding. And when they come together in the solid state, what actually happens is they actually can't get super close to each other. And that's very unusual for a substance. Most of the time when they get into the solid state, a substance pretty much can pack right into one another and they get really close to each other. But because of the way they bond, when water kind of gets close to each other in the solid state, they really can't get super close. And if you think about the density equation, which is our mass over volume, what happens is it creates a big open volume between the different water molecules. and it makes this number larger, which ends up making the density of ice smaller, right? If you divide by a larger number, you end up with a smaller number for the density. And that's a very unusual sort of characteristic of water. Most things in their solid state much more dense than in their liquid state. So as I mentioned before, these are our common units of density, our grams per cubic centimeter, our grams per milliliter, and again, for gases, grams per liter. Here are some of the density values of some common substances. I would say that water's density, and that's liquid water, by the way, and density does change with temperature. The liquid water density, if you ever need it, 1 gram per milliliter is typically the value that you would use for density. So sometimes in problems, you'll come across a situation where like, I feel like I need the density of water, and 1 gram per milliliter is typically the value that you could use. It does change, as we just talked about. Ice is a lot less dense, as you can see there, 0.92 for ice, which is why it actually will float in water, right? It's actually less dense than 1 as well. So, you know, any of these guys are going to sink, right? And obviously, these guys here are going to float, for example, in water because it is less dense. Also, why, for example, if I took, say, a couple of soda cans, yeah, like a Diet Coke and a regular Coke, and I put it into a big sink of water, what will happen to the Coke cans? Will they both sink? Will they both float? Will they do one of each? Yeah, so if you put it in there, the Diet Coke will actually float. The regular Coke there will sink. The reason for that is what's in regular Coke? Sugar, right? And in Diet Coke, it's artificial sweetener. So with all that sugar, it's actually more dense, causes the Coke can to actually sink. Good party trick in case you need one. You know, yes, the Super Bowl was yesterday, but you know, you never know. Next family gathering, you know, you could do those things. All right, so let's talk a little about another common way that we actually do get the volume of a substance. So as I mentioned before, we can get the volume by simply taking a volume reading. We could grab a ruler, do some length measurements. The other very common way that we get the volume of an object is by what's referred to as volume by displacement. And really, volume by displacement is this idea that if you take a container, for example, like a graduated cylinder, and you fill it up with some type of liquid like water, and you would have an initial volume reading when you do that. And if you take a solid object, like a piece of metal, and you drop it into the graduated cylinder, what's going to happen to the water level in there is, will it go down, up, stay the same? Should go up, right? And with their little metal piece in there, and you'll have a final volume reading on the graduated cylinder. So if you take the difference between the initial, that's a long drawing, and the final markings there, that volume difference is the volume of the object. And that would be found by taking the final volume minus the initial volume. So that's a very common way and very easy way that you can basically find the volume of a solid object. You basically just drop it in there, take the difference between the volume, final minus initial, and that will get you your actual volume of that particular object, which is what we kind of see in this example here. Before they put the zinc in, it had a volume of what we got there, 35.5. After they weighed out a certain amount of zinc and they put it in, the volume of water got displaced by that much volume and ended up 45.0 milliliters. So our mass over volume here, we do want to look at significant figures. So when we subtract this, we're actually looking at decimal places here, right? So that would get us our 9.5, which should be 1 decimal place based on the subtraction. But in terms of significant figures, it has, as you can see there, 2 significant figures, right? And that's important because the last thing that we would do here is the division part, where we take the mass divided by that volume, which means we're taking 4 significant figures divided by 2, which means our answer should end up with 2 significant figures. So a lot of times when you do a volume by displacement, you're calculating something like density. A lot of times these significant figures at the end of the calculation is actually based on the subtraction that you do. But you got to remember, since we're subtracting, we're actually looking at decimal places first, which will give you the proper answer to the proper number of significant figures. And then you got to transition from decimal places to significant figures when you do the division part of the density calculation. Question on that? All right, so what is the density here of 48 gram sample that started with 25 milliliters of water and then went to 33 afterwards? So why don't you calculate it up? Got little pictures there to look at. It's pretty good. So we'll start with our density equation, which is mass over volume. We obviously have the mass already given to us here, which is our 48.0 grams. We have our initial volume here of our water in the graduated cylinder. We're going to put that solid in there, and this is going to be our final volume. Once again, if we take the difference there, and I could draw straight lines, the difference there between those two, that's going to give us the volume of the object that went for a swim. So we do want to find the volume that way. So the volume of the object here would be our final volume, which is 33.0 milliliters minus our initial of 25 milliliters. That's going to give me 8.0 milliliters. I do need the 0y because we should be looking at decimal places, right? In this case, there's one decimal place on both of them, which means even though my calculator spit me an 8 out, it actually needs 8.0 to have the proper number of significant figures in this case, right? Our decimal places to gives us proper number of significant figures. That's really important for the last part of the calculation where we take the density, right? And now we take our mass and we divide it by our 8.0 milliliters. And when we do that, we got 48 divided by 8, going to give us 6. And the proper significant figures should be how many in this case? It should be 2 because we do have 3 here and we're dividing here at the end. And this is why it's important that we did put the 0 that should be there because that's technically 2 significant figures, which means we do have to add a 0 here. Now, in terms of the units, do they cancel? They don't. They should still be there at the end. So it should be 6 grams per milliliter. The number always stays with the grams part, and it's always 1 milliliter or 1 cubic centimeter. Any questions on that? So again, it's important to, and sometimes people get a little confused as they're doing it. You got to first look at decimal places here to get the proper decimal places. Then you got to switch gears to significant figures as to how many you got going on there. So again, if you forget the 0 at any of those locations, you will get the wrong answer in terms of significant figures right at the end there. Any questions on that one there? Okay. Hey, and they agree. That's good. All right. So let's try this one. An unknown liquid has a density of 1.32 grams per milliliter. What is the volume of a 14.7 gram sample of this liquid? So we want to think about our density equation, which is density is equal to mass over volume. And we are given the density in this case, which is 1.32 grams per milliliter. We also have the mass given to us, which is 14.7 grams. So if you're not sure, obviously you have the mass, you have the density. So clearly volume seems like a pretty good thing to solve for. And you could solve for volume here. And once again, volume would be mass divided by density. Again, if you wanted to do the DMV triangle there, we have volume is mass divided by density, right? Now, let's just say perhaps can't remember the formula, maybe rearranging the formula is not your thing. This is again where, as I might have said last time, dimensional analysis can also be very helpful to figure out the sort of math part of it or the rearranging part. So because we do have like a density value that has 2 units, that's pretty much like a conversion factor. And we could use the density value like a conversion factor, which means we could flip this around and do milliliters on top and 1.32 grams. Now, the benefit of doing it this way is pretty much we could take a dimensional analysis approach without even really have to thinking about any of these equations and just go, I want to get rid of grams and I want to end up with milliliters, right? So we could just think about our opposites approach. And we would start with the grams, which is the one single unit, which is typically what you start with, right? If you don't have two units. And again, at this point, I don't have to worry about rearranging an equation. I just go back to the dimensional analysis approach, which means I should put grams on top or bottom here to do it correctly. Does need to go on the bottom, which would mean I would want to use the conversion factor of density in this fashion. And now without even having to think about the density equation or really rearrange the density equation, I just rearrange the density equation and solve for volume in this case, without having to actually do it. So again, this is an added benefit of setting things up with dimensional analysis and just thinking about, what units you need to get rid of, what units you want to be left with. And it also sets you up, again, you don't even have to really think about it too hard, because we know, again, everything on top gets multiplied, right? And everything on the bottom gets divided. So now I know I'm going to do the right math here, which is essentially 14.7 divided by 1.32, which is pretty much what that says, right? Mass divided by density. So again, setting it up like this allows you to kind of do the formula without having to do the formula, just kind of keeping things opposite of each other. By the way, it looks like on my calculator, I got a lot of numbers there. 11.13636364 milliliters. In terms of significant figures, we have to look at all the numbers here, right? So they're all important. That's got 3. This one has got 3, which means we should end up at 3 here at 11.1 milliliters. So absolutely, you could rearrange the equation. You could plug the numbers in and get the answer. But once again, if you're unsure about how to do that properly or not super confident, taking a more dimensional analysis approach and just setting up the units works the math out for you without you having to sort of rearrange it. So sometimes it's, very, very helpful. Also, like the previous example or previous example, we're doing how many days. I can't tell you how many people, when we would do a problem like that, would be multiplying by the 60 and 24 instead of being dividing what you need. So again, it just keeps everything where it should be. Any questions on that there? All right. Maybe one last one here before we wrap it up for this chapter here. John took 2 teaspoons of cough syrup for a cough. Syrup has a density of 1.2 grams per milliliter, and there is 5 milliliters in 1 teaspoon. What is the... Okay, so let's take a look. Once again, we're obviously dealing with some density, so we could look at the equation. And also a good idea is to pull out information from the problem. Sometimes it does give you an idea as to where you should maybe try to go to. 2 teaspoons is actually a volume, right? So 2 teaspoons. We also have the density of 1.2 grams per milliliter. And we also have a conversion factor or an equality of 5 milliliters is 1 teaspoon, which we could use obviously to convert our teaspoons into milliliters, right? Which is a useful volume there. When we're dealing with density. So in this particular case, we do have the density and we do have the volume. So we would be looking for mass. And if you rearrange this equation, mass would be volume times density. Again, if you use that triangle there, mass would be density times volume. So again, I'm going to take more of a dimensional analysis approach, so I don't really have to worry about maybe rearranging the equation incorrectly or something like that. So I'm just going to think about it like a dimensional analysis conversion factor type problem, which means, as we've done before, this volume here and this volume here are different. So we do have to put them into the same unit. So that's what I'm going to do first. So I'm going to take my 2 teaspoons. And in this case, I want teaspoons to cancel. So I do need to go opposite, right? Which would put it on the bottom. And up on top should be my 5 milliliters, right? Teaspoons here should cancel. And that's going to give me 10 milliliters. What kind of significant figures should I be having at this point? I should have 2, right? So I should look at this, which is 2. Do I need to look at this? I do, right? It's a conversion from metric to that, which is also 2. We would look at the 5.0. Which means technically we need 2 here, which means I maybe should lay me up a decimal there, right? If I want to kind of clean it up right now. Now that I have my volume in the units I want, I know I want to get rid of the volume here, right? And I want to end up with grams. So I could use the density once again as a conversion factor where I could flip it around and do a milliliter up on top, 1.2 grams. So here, without even have to worry about the equation, I just need to do opposites, right? So I should use conversion factor on the left or right in this case in terms of the density. The one on the left puts the milliliters in the opposite location. So once again, setting up here with dimensional analysis, I didn't even have to bother with the rearranging of the equation here. And now I am actually doing that calculation. Milliliters will cancel. We're going to multiply what's on top. We really have nothing on the bottom to divide by since it's really 1. And we will multiply that. And that will get me 10 times 1.2, going to give me 12 grams, right? And again, I just pretty much did the rearranging of the density equation without even using the density equation and thinking of it more just as a conversion factor. A lot of formulas in chemistry, you pretty much can do that move without having to remember the equation or sort of rearranging the equation. Just think about units you don't want and units you want to end up with and use things as like conversion factors. Significant figures. Right, this has 2, and this one we do need to look at, which has 3, which means we should end up with 2 in this case here, which would be 12 grams. Question on density. Yeah. So I would highly recommend kind of setting up with dimensional analysis. Again, you can just plug and chug into the equation, but I've seen that equation rearranged incorrectly a lot of times. People will do it. So this is just another sort of safeguard that hopefully will allow you to set things up correctly and do the math correctly. Any questions on that there? All right, that is density. That is specific gravity. And it has an X on it, so clearly we're not going to do it because somebody put an X on it, so we're just going to not worry about that. So that we're going to continue on here. So as I mentioned, I think last time, and as I put an announcement out today, I posted up a pre-recorded lecture for chapter 3, which is energy. I think it's only like an hour and 20 minutes or something like that. So make sure you watch it. Make sure you take notes like a normal sort of lecture. I think you'll even see me in that lecture. I think that has a camera on that one. So if you do have questions, make sure you ask it. You are responsible for that. It will be on the first exam that's coming up. But just because of the holiday coming up on Monday, and try to keep us on pace. So hopefully next week as well, you know, lab wise we'll be not too far off of the pace that we need to be. We're going to go ahead here to chapter 4. And again, we're not going to officially lecture on chapter 3 together, but there is again a recorded lecture that was done in person. And so make sure that you do watch that and look at it. All right, so let's go to chapter 4, which is atoms and elements. So in this chapter, we're going to talk about atoms and elements, as it says. So we will talk about elements and symbols and formulas. We will also talk about atoms, and we'll talk a little bit. We're not going to go into great detail, but we'll talk a little about some experiments that helped us understand a little better about the structure of the atom. We will talk about atomic number and mass numbers and what those mean. And we'll also hit the periodic table, I think, in this chapter as well. And we will finish it up. If there's not enough stuff crammed into this chapter, we will talk about electrons and electron configuration and how to write all that stuff. So a lot of stuff sort of happening in this chapter. So let us get going on it, I think. So atoms and elements. Elements are really the sort of, right here behind me, they are the basic sort of building blocks of everything. You could think of elements again as sort of like the alphabet. There's only so many letters we have, right? But we can make all kinds of words, right? Depending on the combination of letters that we put together. It's the same idea here. There's only a certain number of elements present, but different combinations of elements, different combinations of the same elements and different amounts give us different compounds that occur as well. The atom is the basic unit of all elements. And as we'll talk about, the atom basically contains even smaller particles. And there's protons, which are positively charged. There's electrons, which are negatively charged. and there are neutrons, which have basically no charge. So the basic representation of all the elements that are behind me here on the periodic table are an atom of that particular element, and they have protons, electrons, and neutrons. As we will talk about, all elements have protons, electrons, and neutrons, except for actually hydrogen. Hydrogen actually only has protons and electron and does not have a neutron, but all other elements pretty much have all three of those things. So when we talk about elements, they do have symbols, and element symbols are basically one of two things. They are either a single letter symbol, and if it is a single letter symbol, you should always capitalize it. So for example, K is potassium, and it should be capital. C is carbon, which should be a capital C. There's also two-letter elements, which you should always capitalize the first letter, but not the second. So like aluminum is AL, capital, not capital. That is important because you could write something like this, CO and CO. They both do not mean the same thing. Capital C, lowercase o is cobalt, which is an element. Capital C and capital O is carbon monoxide, which is very, very different. So if you're a person that writes capital letters for everything, do not write capital letters for when you're writing symbols, because you might actually be writing something that you do not mean to write. But they should always, again, two letters, first one capitalized, second one not. And if it is a one letter symbol, then it should be capitalized. Elements are pure substances. And they cannot be broken down any farther by chemical means. And pretty much it's as far back as you could go. So you could definitely take some elements, combine them together to make compounds. But when you go backwards, you can only break those compounds back down into elements. Now, elements, for example, can also be molecules. And there are certain elements that how they naturally come are as actually molecules, which means they come as twos. And there are some elements, how they naturally come is like hydrogen comes as H2, nitrogen comes as N2, O2 for oxygen, Cl2, F2, I2, Br2. These are all elements, and this is how they naturally come when they're not combined with anybody else. So like hydrogen comes as hydrogen gas, and oxygen comes as oxygen gas, nitrogen comes as nitrogen gas. Basically, two atoms of hydrogen bound together, two atoms of oxygen bound together, two atoms of nitrogen bound together. So that is always how they come. These are what are sometimes referred to as being diatomic molecules. Di meaning two, atomic meaning atom. So they're made up of two atoms, basically. Most other elements come as monoatomic, which means one atom, basically, is how they come naturally when they're not combined. By the way, also a misconception people have is these things have charges. They do not have charges if they're by themselves. So if you have something by itself, it does not have a charge. It actually only gains a charge when like a metal and a non-metal come together and actually do something to make a certain type of bond. But if you have just a piece of copper by itself, has no charge. A piece of calcium by itself has no charge. So they're like neutral, basically. But these are certain elements that also come as molecules. So speaking of compounds, which we might see as well, sometimes people are confused by sort of the definition of compounds and molecules. So let's just sort of clear that up just to make sure, just in case we have not. A molecule is the basic definition that means you need to have at least two or more atoms present. A compound is you need to have two or more atoms of different elements present. So that is a slight difference in those definitions. So the way I remember it, or sort of tell people to remember it, is it's not very restrictive in terms of a molecule for something to be called a molecule. You basically just need to meet the criteria of, do you have two or more atoms there? Those could be 2 or more atoms of the same element. They could be 2 or more atoms of different elements, and they would be considered molecules. Now, in order for something to be a compound, you have to have still 2 or more atoms, but there's a second part to that, that it has to be 2 or more elements involved, which means that these guys here are elements. They are also molecules because there's 2 or more atoms. Are these guys compounds? These guys here are not compounds because they all contain the same element, right? Now, if you have something like water, H2O, water, is it a molecule? It is a molecule, right? Because there's 2 or more atoms, right? Is it a compound? It is a compound because it contains atoms of hydrogen and oxygen. Is it an element? It is not an element. So that is, again, the major difference between something that's a molecule and something that is a compound, is that difference. Speaking of what we were just talking about, as far as you could go, you can't break it down any further, but you can very easily take water, run an electrical current through it, and do a little hydrolysis there of water, and you can break it apart into hydrogen gas and oxygen gas, but that is, again, as far as you could go. So you could take it from a compound to elements, but as soon as you hit those elements, that's as far back as you could break it apart any further. So electrolysis of water is the right term there, not really hydrolysis, but the electrolysis of water. Any questions on the difference there between those things? Yeah.
Would the HCl it's a molecule compound or a molecule by itself?
Yeah, so most people would probably refer to it as a molecule of water, but it is also a compound because it does contain those 2 elements. So you can refer to it either way. These guys up there, like the H2, the O2, and all those, you could refer to them as molecules, diatomic molecules, or just molecules. You could also refer to them as elements, but you should not refer to them as compounds because they don't contain other elements. There we go. Other questions? So here are some of the elements and their names, and some names do come from a variety of sources, historical names, places where they were found. That's how you get things like Californium. I'm assuming California. Berkeleum. I'm assuming somewhere there near Berkeley. Francium. All those kind of things. And some are just other sort of names. So uranium, titanium, chlorine. Here are some of the symbols for those guys. As I mentioned before, if it is a 2-letter symbol, you do need to capitalize the first one and the second letter. Carbon, sulfur, nitrogen, neon, some other symbols that sometimes people have trouble with. AG is silver, yeah. AU is gold, right? K is potassium, right? Na is sodium, yeah. How about PB? PB is it's lead, actually. PB is lead. How about SN? That is tin, yeah. ZN is zinc, yeah. My favorite element, Se, is selenium, right? So it's good to know. So, some have some weird symbols, and it's just really sort of the root of where they kind of came from. For example, iron, right, is Fe is iron, right? So that is the symbol for iron. Copper, sometimes people get wrong. They go like copper, it seems like it should be Co, but as we just talked about, Co is cobalt, right? Which is that. Copper is actually Cu, right? Is copper. So people always ask at this point, do I need to know the entire periodic table? And the answer is, of course, right? It's a chemistry class, but no, I'm just kidding. Most of it, and if you don't have some recognition, it's probably a good idea, because I think after this chapter, we're going to roll into some naming and stuff like that, where there's all kinds of rules about how you name everything. So if you're still struggling to figure out, what the symbol is for a particular element, it's just going to make that a lot harder for you. I don't know if this is helpful or not, but usually to the left here, we deal with a lot in terms of symbols. Kind of here and up to the right is a lot of stuff that we deal with. I would say definitely through this first row and then kind of down in this area and here as well. So not too much down here, except for maybe uranium, which is radioactive element right there. Really not too much in this area. It actually varies depending on where in the periodic table was actually printed. You may have some periodic tables where there's like nothing here. This is usually where they put like elements. We're not sure we're going to make real elements or not, so they put weird symbols here. So usually on this sort of row, not too much happening. Not too much happening down here. This is where you get down here, by the way, where you have a lot of kind of man-made elements, which have those names like Einsteinium and those type of things. But yeah, definitely to the left, kind of to the right. This little pocket in here is something that we come across a lot. That's tin, which is SN. SB is actually antimony. BI is bismuth. And there's our lead. So this little 4-pack here sort of pops up a lot. And like I said, kind of through probably right around here, chromium, iron, cobalt, nickel, and then into this area as well. Not so much in here, but kind of the top-ish, and then kind of going down into here, and then kind of upwards is where a lot of them are. So I would say if you don't have recognition, try to get some recognition. It's going to help you obviously in the long run when we get to those things. So aluminum, here's some of our other symbols along the way. And again, you can see where some of these symbols do come from. These are really sort of the historical names, or sometimes they're Latin names and stuff like that, where these sort of symbols do come from. By the way, Hg is mercury, and that does pop up a lot. So Hg as well. So here's some of those symbols and why we use some of the letters there along the way. E, again, capital F, lowercase e. Magnesium is capital M, lowercase g. Zinc is capital Z, lowercase n. And lithium is capital I, capital L, and lowercase I in this case. Any questions on any of those there? All right, so take a moment and see if you come up with these names here. Yes, sir? It's the D. It's BE, as in Edward. Yep. Okay, so let's take a look. So phosphorus there would be P. AR is argon. Mn is manganese, not magnesium. Be is beryllium, and K is potassium. So the short answer, I guess, is you do need to know these elements and their symbols. And again, it's going to be very helpful when we get to chapter 6, I think, is when we start talking about nomenclature, which, since I think we skipped chapter 5, is coming up after this chapter. Yeah, so try to get that recognition of those symbols and the names, because again, it's just going to make the sort of naming part a lot easier. Any questions on that there? Okay, we're going to talk then about the atom and the structure of the atom, and some important sort of events that helped us understand a little bit more about the atom and where we find those subatomic particles like protons, electrons, and neutrons. So the atom is, again, basically the smallest particle that can exist for a particular element. As I mentioned earlier, it does contain protons, electrons, and neutrons. And early on, Dalton came up with what is referred to as Dalton's atomic theory, and that's John Dalton. And he was an interesting guy. He liked to go bowling on Thursdays, and he wrote the weather every day, his life, what it was. But he came up with this idea of what's referred to as Dalton's atomic theory. And Dalton's atomic theory is not correct in all aspects of it. So if you remember at the very first day, perhaps, we talked about the idea of a theory, and a theory is something that may not be perfect all the way through, can be found later to be maybe not correct in certain aspects of it. And that's what happened with Dalton's atomic theory. There's certain parts of it that is not so correct, and there are certain parts that are still correct so today. So let's talk about some of these ideas here of Dalton's atomic theory. He said that basically all matter is made up of these tiny sort of indestructible particles that he called atoms. He said that all atoms of a given element are identical to one another, and also atoms of different elements are also different from one another. He said that really atoms of two or more different elements come together to make a compound, which is correct. A particular compound always made up of the same type of elements in the same ratio. So really what that means, for example, is if you had something like water, H2O, you always have two hydrogen atoms and one oxygen atom, no matter where you grab your water from, if it's H2O. And it also has the same sort of mass ratio as well, because oxygen is about 16 grams, hydrogen is about 1 gram each. So that's basically 2 grams of hydrogen for 16 grams of oxygen, are really every water is made up of about 1 gram of hydrogen for every 8 grams of oxygen that's present in this particular case. And another important thing that he said was that a chemical reaction really only involves the rearrangement of atoms. We don't lose atoms along the way. We don't create atoms along the way. They basically just break apart all the bonds that hold them together, and then they reassemble on the other side in new compounds and stuff like that. And basically what that means is the basis, and that's the law of conservation of mass, is the basis for a lot of things that we do in chemistry, like why we balance equations. That means that if we start with like 6 carbons at the beginning of the reaction, we should still have 6 carbons on the product side. They may just be in different compounds on the product side than where they started with. Law of conservation of mass means that if I started with 6 carbons on the starting side, because each carbon is 12 grams, I'll have the same 6 times 12 on the product side, just in different compounds along the way. So one important thing about reactions is we never create new elements. We never lose elements along the way. We just basically rearrange everybody. In nuclear reactions, which we don't talk about, which is chapter 5, you actually do create new elements along the way. But in normal chemical reactions, which is what we talk about in this class, you don't do that. So we have the conservation. So what parts of this theory is really not so correct? A couple of ideas. The idea that atoms are indestructible, and the idea of nuclear reactions sort of disprove that a little bit. You can obviously change one atom element into another element in a nuclear reaction, not in a chemical reaction, which is what we talk about here. That doesn't happen, but you can do that. And the other main thing that is not so correct is this part of it, which all the atoms of a given element are going to be identical to each other. They will have the same mass, they will look the same, they'll be the same size. And the existence of isotopes, which we'll talk about a little bit more in this chapter, disproves that. And what isotopes are the same element, but they have different masses. So these are really the same element, but different masses. So clearly, if they have different masses, they cannot be identical to each other, right? Somebody's got to have a little bit more weight than somebody else. That means they have different particles present as well. So those two parts of Dalton's atomic theory is not so correct. And really the existence of those isotopes sort of disprove the idea of all elements or atoms of the same element are going to be identical to each other. So by the end of the 1800s, there was a lot of experiments that were done. And as I mentioned before, even though atoms are very, very small, they were found to have an internal structure, which are sometimes referred to as subatomic particles. And those are our protons, neutrons, and electrons. And once again, those are our positively charged particles. These are guys with no charge. And our electrons are negatively charged particles. So there was a lot of experiments that were done along the way to help us sort of explore each of these sort of particles and really have an understanding of where they were found within the atom. And one sort of important idea is something that I think we might have talked about previously, but just in case, it's really an important idea in chemistry, which is opposites attract, which is sometimes referred to as electrostatic attraction. So things that have the same type of charge do not want to be near each other. So if you get two positive guys like we see here, they are going to want to head in the opposite direction. If you get two negative guys near each other, they also are going to want to kind of head in the opposite direction. But if you actually get some opposite charges, they're going to be actually attracted to each other. And that sort of attraction, which is the electrostatic attraction between the positive and negative charge, is a really hallmark sort of interaction that happens all over chemistry. Almost all interactions of how one molecule interacts with another molecule is through like the positive side of one is attracted to the negative side of another. So that sort of attraction is very, very much seen a lot at times in chemistry. And when people were exploring sort of the atom, they used that to their benefit because a lot of experiments that they did involved radioactive particles. Like, for example, alpha particles, which are positively charged radioactive particles, beta particles, which are negatively charged particles, radioactive particles, and they also use gamma rays, which are basically have no charge. And you can kind of almost visualize that it's kind of like a proton sort of beam, an electron beam, and like a neutron sort of idea here. And a lot of experiments use these radioactive particles and the use of something like an electrical field, where you have a positive side and a negative side to an electrical field. And when you have a particle and you're not really sure what the charge is, for example, of that particle, and you expose it to an electrical field, you can make a pretty good guess as to what type of charge that particle has. If I shoot a particle through this or a beam and it folds up towards the positive side, that would probably mean that that particle is what type of charge? Negatively charged, right? Because it was kind of attracted to the positive side of the electrical field. If you shot some particles and they kind of bent towards the negative side, you would know that those particles most likely had a positive charge. And if you shot some particles and really it was unaffected by the electrical field and just kind of went straight, ignore my non-straight line there, but imagine that it did go straight, you could probably assume that it has no charge sort of associated with it. They also use a magnetic field, which has a north pole and a south pole, works kind of very similar in terms of bending things with charges. So these type of particles were used a lot to explore the nature of the atom. And by taking advantage of that sort of electrostatic attraction, they really can explore, things like electrons, protons, and neutrons. And I think we're going to lay it up right there and talk